coming up. It's my pleasure to introduce our second speaker, Francesco Borrelli. He's a professor at UC Berkeley and also the co-director of the Hyundai Center of Excellence there. Among others, Francesco is an expert in market control and applications to automatic vehicles and energy systems. And I think he's going to present perspectives from that point of view and learning to predict and control.
Thank you, Melanie. Thank you, the organizer, for inviting me. Sorry, George, you heard this already. The last 10 minutes are new. You'll see a lot of videos in this talk, hard work of my graduate students and my industry sponsors, in particular, Hyundai and Yang Liu and Alex Hao and Nextracker. I'll decide to divide the talk into three parts. First, my classification learns. It will help you understanding our contribution to iterative learning, predictive control, and then I'll conclude with some idea what is new versus old, and some practical applications of learning. So I classify learning into three big areas. Skill acquisitions, where you don't know how to do certain things, you practice, and at the end you're able to kick a ball mid-air. Okay, you didn't know at the beginning of the practice, at the end you'll be able to do it. If you keep kicking balls mid-air, then at the end of your career you become really good at it. And then I'll call this performance improvement. Okay, you knew how to do it, but you get better and better. And then if you keep kicking balls, then you store your policy and you go in open loop. Okay, I call this computational load reduction. Okay, and you can see that there's no totally open loop. Okay, this is definitely an oversimplification. So different names in reinforcement learning. You could hear learning from scratch, iterative learning, learning from memorizing. If you talk to a neuroscientist, this is way too simple. However, I claim this is actually simple enough for our community because you can actually classify most of the body of literature in learning into these three areas. Skill acquisition was actually the hardest part. A lot of reinforcement learning community is focused on this. You have no clue how to solve the task. It's very hard, dynamically challenging. And then you have to use expert demonstration, transfer learning, trying to find the feasible guess. Performance improvement is where probably there's most of the literature, most studied. If you read a control paper, they will say, you will read an assumption, assume that there is a positive invariant set. Okay, it means that assume that you have a set of states for which you know a policy that bring you the terminal goal. If you read a reinforcement learning paper, you will read suboptimal successful trajectory from a demonstrator available. Okay, this is the performance improvement part. Computational load reduction is all the community trying to go from optimization to lookup tables, explicit model predictive control, neural networks on chips. So I'll focus on these three main areas, and I'll give you my perspectives. However, I want to mention that when the learning, really what is popular with the hype, is really mixed, these three areas mixed with the use of neural network to do one of these three things. Replace the state with the output, especially from camera. Or replace, if you have a robot and you're moving in an environment, you replace the model of the environment and the agents around you with a neural network. Or actually replace the state observer, the model of the agents, and the control with a neural network. And this is called end-to-end learning. I'm not going to comment on this. I'm not going to discuss this. I'll comment this at the end of the talk. I'll just focus on these three first areas. And if you know me, I work a lot with cars, with autonomous vehicles. I decided to give an example of which one the three areas by using a race car, a 1-to-10 vehicle that is trying to do complex maneuvers. Okay, this is a car that is learning how to drift parking. It's complicated because it's the nonlinear dynamics interaction with the tires. You have constraints. At the end of the training, you'll be able to drift park. Okay, and this policy works only for that initial state, only for that ground, only for that vehicle, only for the precise location of the obstacles. Okay, nothing is transferable at this point. A performance improvement for a vehicle will look like this. You have a car and you ask to find the race line, actually to race around this track in minimum time. You don't know much about the model. You're trying to learn the model and the race line. And as you see, as you keep going over and trying exploring your models, at the end, you'll be able to, at lap 31, you're able to do this in 6 seconds. And if you see the perspective from the vehicle, it's actually, you're reaching the limits of the tire's behavior. Okay, so you are, I think soon you will see how this corner is cut and reaching, I think, 15 degrees of roll, a 1 g of acceleration. Okay. As you have learned how to, these are experimental data, as you have learned how to go faster and faster on this track, you see on top the lap time, and at the bottom the computational load of the CPU, you actually stop predicting. There's no need of making forecasts anymore. Use your local data around you, and now you look up the policy, and you can see that the CPU load, this is on the bottom here, you'll see the CPU load is it's a factor of 10, sorry, less, and you're still taking the same time to raise the vehicle, okay? So what are we learning and how we do this? The mathematical model we use is pretty simple. You have 3 blocks, the one in red and in blue. In blue, you go from inertial frame to, from body frame to inertial frame. And in red, you have the 3D rigid body equation of motions, okay? What is challenging, so it's an 8-dimensional model. It's only a planar model, x, y, and heading angle. What is challenging are these forces. I just finished teaching a class on vehicle dynamics. Half of the semester we spent on these 2 functions. Lateral forces and longitudinal forces to the tire is a function of slip ratio, slip angle, friction confusion, and load transfer. And there are entire books on how this force should look like. But if you, even without knowing much about racing, you understand that if you have this shape, you want to work at the peak of the forces, okay? This is called the stable region. If you go on the other side, your car becomes unstable and you will crash your vehicle. There is a constraint that is challenging. Actually, you cannot get that the sum of the Fx and Fy has to be less or equal than mg if your friction is 1. The other thing that you want to learn, so tire dynamics are hard, and that's what you want to learn. The other thing you want to learn is with the race line, which is, again, a very complex function of your dynamics, of your tire and the track shape. So we do this very simple idea, which we call iterative learning model predictive control. And in the next part, in the second part of the talk, I want to give you 10 minutes of very simple overview how this works. You start from trying to solve a task, looking for which is a long horizon or an infinite horizon, and try and look for a set of feedback policy that minimize some cost functions subject to your dynamics and constraints. And in the MPC community, you say this is too hard because I can't solve that long horizon task. You solve this over a finite horizon by repeatedly solving a set of short horizon control problems, and you apply only the first policy pi 0 with the current state x of t. When we teach model predictive control, we say that we have to do this properly, otherwise it's not going to work. Because you're short-sighted, you actually won't be able to go to your goal. And so we teach people that you have to pick the right terminal cost, and you have to pick the right terminal constraint. In particular, the terminal constraint has to be a control Lyapunov function. It's a set from which there is a policy that brings you to the goal, and the terminal cost has to be a control invariant set. And the terminal cost has to be a control Lyapunov function, a function that in closed loop decreases more than the stage cost. So what does it change in this iterative scheme, in this reinforcement learning, with this reinforcement learning perspective? Well, it changes that now you have historical data of the same task at previous iterations. Okay? And so what you can say is, well, use this data to learn the cost, learn the safe set, and learn the dynamics. And very simple idea. And so what I'm going to show you how simple this is. Let's assume I know perfectly the model. I'll comment about this later. Everything is deterministic. And let me show you actually how you compute this terminal cost in the safe set. Super simple idea. Okay? You have, on our website, you have a set of 10 papers. So there is the uncertain version, the adaptive version, and the chance constraint version of this formulation. But the main idea is very simple. If you have a successful trajectory of a task, and this is your state plotted in 2 dimensions, this is a control invariant set. Everybody agrees? If I am on a state, there is a policy that brings me to the goal. Okay? So this is we call it sample safe sets. Okay? And the next iteration 1, you solve a model predictive control with forecast where you try to land in one of the states. Okay? And so you go in a moving horizon, so what you predict in open loop is different what you do in closed loop. You apply the first input, you do another forecast, and so on. And at the end of the second iteration, you have another set of states. The union of the 2 states, the set of states are it's a new updated sample safe set. Okay? At iteration J, the sample safe set is all the union of the sets which were successful. And for constrained linear system, if you take the convex hull, this is a control invariant set. As simple as this. Okay, use this convex hull of successful trajectories at previous iteration as your terminal set. What about the cost to go? It's also very simple. If you have a successful trajectory, for each state you compute the realized cost, which is the costs to go to the goal over the closed loop trajectories in that iteration. That is actually a control Lyapunov function by definition on this sample set. And if you have multiple iterations, so here you see this is a one-dimensional state, and your Q function, you go from xs to the right to x final to the left. You're going to have a lot of points at different iterations. What you're going to take is the epigraph of the convex hull of all these Q points. Okay? And so you can prove this is a so-called barycentric approximation. This, for constrained linear system, is a control Lyapunov function. As simple as this. This is the basic idea of what we call iterative learning MPC. You have an MPC schema. You minimize over the input sequence as well as the lambdas of your cost to go, subject to the safe convex set as a terminal constraints and the Q function that I showed you before. You can show that for linear systems. For constrained linear system, if you were safe at one iteration, you'll be safe at the next iteration. If you were, the performance does not degrade, you will always go better and better. It will do the same as the previous iteration. And for a constrained linear system, you can also show convergence to the global optimum. So what is different from all this body of literature on reinforcement learning? I always get asked this question. First of all, I still have to read around 3,000 papers from last year. But as I keep reading, I call this thing YADP, yet another approximate dynamic programming. And there's a good reference from Bertseikas, Connected MPC, and ADP, and approximate dynamic programming, and also a good blog from RECT. A couple of things. First of all, is a continuous state formulation rather than a discrete state. You do have constraint satisfaction. Most importantly, these Q functions are constructed locally as the MPC explores. Okay, this is the core difference. And also, because we use a barycentric approximation, they're exact at the sample points. So I've met a few times with Professor Bertseikas, and I think the best way to look at this is actually a safe and efficient aggregate approximate dynamic programming. In aggregate approximate dynamic programming, you need to go from this high-dimensional space to an aggregate space so you can solve dynamic programming. And so here the idea is basically let MPC explore and find aggregate states. Okay? And that's the first part. And the second part, then don't use a linear approximation of your feature. Use actually a barycentric approximation of your feature. Just add the convex constraint. Okay? And so, and again, so if you take the uncertain case here, at each iteration you get these blue points are the state points. This you can see their convex hull is going to be the aggregate states. Okay, and you have a barycentric approximation function on top of these aggregate states. So let's go back to race. How does this problem looks like? You have minimizing time, initial state, terminal state function. We applied the technique that exactly I showed you before. Let's look a little bit at the model. We use a linear model here. And the way we do this, we linearize the kinematic equations along the previous equilibrium point. And we use a simple kernel function for the dynamic equations. Okay, local linear regression, which is where the k is identified, where the parameters are identified in real time using historical data. Okay, there's actually this idea of mixing physics-based versus data-driven models. I think it's quite interesting, and there's very good work from Melanie, Angela, and Claire in this area, and I think this is probably one of the most interesting things in this area. You see data of the performance as you race going down, your lap time is going down. The interesting part, this works on every race, the racetrack, okay? So that's the same algorithm works on every racetrack. The same algorithm works on every car, okay? So this is our, is there a video here? Is there audio? Uh-oh. So you want to hear the peak, and to hear that you're at the peak of the Pacheco, the time models, you need to hear the scratch, okay? And if you hear a whoosh sound, then it's too you're on the other side, okay? You see it at the end, this is really where the convergence is achieved. You can see it's cut in the corner and going at the maximum tire forces limit. So, by the way, the code, exactly the code that runs on the little car and the big car is on GitHub on our website. Do you need to this safe set? I've seen a lot of RL papers where the cost function is interpolated outside. You do need the safe set. Okay, you can see if you remove the safe, you have to do this in simulation. We don't do this on the big car. You're going to crash your vehicle. Okay. Do you need forecast to learn? Yes. Okay, you're going to not, of course, now you can perturb this and explore and take your chances, but because you enforce a safe set, if you don't forecast, you're not going to learn. Okay. And actually, there's a very interesting work where we have shown that how much you need to forecast is linked to the rank of the controllability matrix of your system. Do you need to predict once you've learned? This goes back to the vehicle that is solving a QP in real time, is an MPC updating the model. At some point, it reaches convergence. Okay? Why don't you take the Q? At some point, you have the Q, the X's, and the U. Why don't you take the stored data and solve this simple linear program, and you get a reduction of 10x of your CPU, okay? So you're stopping prediction, you're going in open loop based on your historical data, okay? Well, 8 minutes left. Let me conclude with some ideas on what is new versus old, and where do we need all this learning. We all agree vocabulary is new, right? If I was writing papers on simulation, system ID adaptation, my students had to write paper with episodes, training, learning, skill acquisition. It is new, more seriously, the use of data to compute this Lyapunov function safe set. I mean, here, it is different. I'm not finding the level set of an AJB equation. I'm not finding the fixed point of a set valued iteration to compute the safe set, which is my favorite method. I'm actually taking a bunch of points and taking convex hull. And these points come from experimental data. This is new, okay? Most importantly, what is different, I think, and I've seen this in my professional work, is actually this remote to cloud architecture, which enables learning. Today, OEMs, can update their controllers, the transfer function on all the vehicles around the world. Okay, you can rewrite your PID on Amazon Web Service and push it on all your thousands of vehicles. This is, a few OEMs have this. All OEM will have this in the next 5 years. It's called over-the-air updates, and you can do over-the-air updates of your control policy. And Nextracker, what we do, we build utility-scale solar power plants. These are huge solar power plants. They are the video that you see here, this is one of our largest one. 9 square miles in New Mexico. This is a 750 megawatt power plant. Okay, so this little rectangle that you see, these are independently controlled rows. Okay, they track the sun. There is a tracker that we deploy, and each tracker is 10 PIDs. Okay, and now there are 2,500 rows in 100 megawatts. So basically, I have 1 million PID per gigawatt that we can override and change, retune it from Fremont, California, okay? Why would you do that? I'll tell you in a second. But these PID are all connected through the cloud, and we have built and extract all the architecture, and these are very low latency. You can do this in semi-real time. We need this learning, okay? That's my last thought today, and I've been thinking about this for now many years, together with Ben. When I mean learning, I mean a combination of all this that I showed you plus this neural network. Let's all agree that the idea is for autonomous vehicle of taking localization, agent behavior modeling, motion planning, and path following, and replacing with a big neural network is not a good idea. Okay? I know it's embarrassing I have to say it, but it's just not a good idea. Okay? So where do we need this? And I stole this slide from Ben, where he tries to see what is good about machine learning and what is not. And so let's go back to solar power plants. This is it's simple. It's not as cool as robotic manipulators. But the point here is that now if you can point a camera at the sky, you can look at the clouds and you can forecast where clouds are coming. You can forecast the shade on each tracker. You can actually have a geometry of your ground, and you can change the angle of the tracker independently. Okay? And you can do this in real time.
Technologies to maximize energy yield for new and existing power plants. How does TrueCapture harvest up to 6% more energy? By enabling each individual tracker row to compensate for variations in geographic features, terrain, and changing weather in real time.
So this is one of the things I'm most proud of in my professional life. This is deployed. These are all the solar power plants around the world. We have a fleet of 18 gigawatts. It's 6% measured by independent contractors. It's real-time control using machine learning. This, a 6% on 18 gigawatt fleet, that's 10 coal power plants. Okay, so that's real and that's simple. It's not as cool. The next thing that I want to change is this. This is when you and your Uber driver of your self-driving car will buy their own car. They're gonna, there's this sticker, right? This is how much miles per gallon the car uses. And the way this is computed is obsolete, right? This is a single powertrain control for an average profile for an average driver, okay? And there's no need of doing this anymore, right? So what we did for the past 2 years, we have taken the most fuel-efficient car in America, the Hyundai Ioniq, is 58 miles per gallon. The powertrain is quite complex. It has a battery internal combustion engine, switches, and we have rewritten the powertrain control as we learn the data from the driver and the road. Okay, and so this is we took the a typical commute, long commute in Silicon Valley from Fremont to Berkeley, back and forth. You see the pattern. We did this for a year. We learned the traffic patterns. We learned the driver models. Okay, and we have basically rewritten the controls on the fly, showing that this car, which is already the most fuel-efficient car, can actually become 10% more efficient. This is measured data on the road and on dyno. And what changes is the way you deplete the battery and balance the internal combustion engine. And you can do more interesting things. This is a new project we have on next to LA, where there are 5 cars going around, sharing data, learning the traffic light patterns, and nicely driving through the cities while saving fuel and being safe. I guess this is my conclusion. I wanted to tell you my classification of learning, a little bit our simple idea of iterative learning, predictive control, what is new, and who needs all this learning. Thank you for your attention.
For the nice presentation. Now we have time. You're also perfect in that. So we have 3 minutes time for questions. Can we? Okay. Pablo's done.
A very nice talk. What happens? How would your approach extend when you take the car out of the track and onto the real streets?
The vehicle, remember what I've said was there was the fundamental work, and then there was the part that we were doing environment model. Okay, the environment model that we have is very simple. It's a lateral left and right constraint. Okay, as long as your environment model is a lane, that is going to work, which is not the real world. Okay, yeah. Oh yeah, absolutely, absolutely. Oh, I see. If you confine to this is part of this what we are doing in the cities here. If you confine to a simple environment and you have a daily route, okay, you can compute the powertrain cost to go for your daily route. This is exactly what we are doing, and that's what I'm advocating for. A very good question.
Yes, hi. So your approach of approximating the safe set as the convex hull of the safe sample paths that you observe, does it require any assumptions on the problem geometry to ensure either the safety or the
if you take a convex hull, safety is only guaranteed for constrained linear systems, linear dynamical systems. So what we do for the nonlinear case, we actually take convex hull of each episode, and we do the union of convex hull. rather than, so this has turned out to be, then of course when you do optimization, you need to do some form of choice or mixed integer optimization or a simple, choice.
Hi, my question is that you have showed 8.8% improvement in terms of fuel efficiency where you have used learning for the powertrain to improve the powertrain controller.
Yes.
My question is that you have showed a specific drive cycle, but is this improvement is agnostic to any drive cycle or?
No, very good point. This is one of the biggest problem of testing this type of techniques, right? Okay, I got 8.8% on the Fremont to Berkeley route. What about in a different route? Okay, so I don't have data with that. That's why we picked the most common route. That's usually the way to do. You take the most driven route in the Bay Area. Where is the advantage? The advantage is one, the way you discharge the battery versus use of internal combustion engine, and this depends on traffic patterns. If there is nobody in front of you, and if you are a very boring driver, there's nothing to gain there. Okay.
Thank you very much.
Maybe time for one last question, if there is one.
Hey, I have a question about the computational reduction at the end.
Mm-hmm.
So it seems the algorithm is based on the convex hull of all the accumulated data. Is there any way to throw away some old data that are less useful?
Yes, absolutely. Very, very good question. It's this, as I've shown, it is, be careful this, there's a lot of different versions of this, but this is the right way to do it. It's not the convex all the data, it's the weighted the weighted previous stored input, where the weights are the weighted solve this linear program, which minimizes the barycentric approximation of Q function subject to the convex hull constraint. Okay, so yes, absolutely. There are lots of interesting things to do here. Do you need to store all Q, or Q, X, and U? What if you remove? There's the students. You can do interesting work on sampling-based method, trying to remove a lot of data and see how much, using sampling theory. Given you remove 10% of the data, how suboptimal you are. A very good question. Yeah.